For this last video, we're going to talk about fission and fusion. Okay? Let's pause that for a minute. So again, I find this to be more content that I think is just good to know to create an informed citizenry. Okay? So we're going to talk about how we get power and energy out of nuclear decay processes. Okay? And I realized, let's see, yes, I was one slide ahead. Okay, here we go. So fusion and fission. So if you recall, we talked about iron 56 being, as it were, the most stable nucleus. Okay, and so because of that, everything below iron 56, so everything that's lighter than iron 56, will undergo fusion. And so that's the combining of two light nuclei to form a heavier, more stable nucleus. Okay? And if you recall, that binding energy calculation we did, right, when we force two light nuclei together to form a heavier, more stable nucleus, we get a ton of energy out of that situation. Okay? And so fission, on the other hand, if we look at everything heavier than iron 56, those things will want to split. Okay, so splitting a heavy nucleus into two nuclei with smaller mass numbers, which of course will also release energy. So we get an energy release from the fission process above iron 56, and we get energy release for the fusion process below iron 56. And both we have used, or really we've predominantly used fission to create energy in this world. But there's a lot of really promising research on using fusion, which is far less dangerous and toxic than fission. Okay? And I'm not going to spend a whole lot of time talking about the atomic bombs, but those are all from fission of plutonium. Okay, so let's talk about fission. Okay, so splitting two nuclei, or splitting a nuclei into heavier nuclei with smaller mass numbers. So the most abundant fissionable material in the world is uranium-235. Okay, there are other fissionable materials. One I just mentioned, plutonium, which is predominantly used in the bombs. However, uranium-235 is the principal material used in nuclear power plants. Okay? It exists in very low abundance naturally, so you might have heard of things called breed reactors. And a breed reactor is where people take pitchblende, which is a mineral containing a natural amount of uranium, to separate out that uranium-235 and generate a large amount of it. Okay? And so now this uranium-235 will undergo fission on its own. However, to get a really bang for your buck out of this thing, if you slam it with a neutron, okay, it will create this unstable nucleus, this uranium-236, because you're slamming one neutron on there, and that will decay into smaller, more stable nuclei. So here I know the font was small here, but that's showing you that temporary uranium-236 that gets created from uranium-235 from slamming it with a neutron. And this material will undergo fission. It will start releasing these lighter nuclei, but also more neutrons and energy. And if you have what's called critical mass, you've probably heard that term before, then you will get an uncontrolled chain reaction where this will just go and go and go and release a buttload of energy in the process. Okay, so this process is showing you the chain reaction. Okay, where now you no longer need to slam a neutron into that uranium. There's enough neutrons that are just generated from that process to sustain this chain reaction. Okay? And so the critical mass for uranium-235 is something like 50 kilograms. So if you have 50 kilograms of uranium-235, you will have achieved critical mass, and it will just go through this chain reaction, whether you want it to or not. Okay? So the way that a modern nuclear reactor works, okay, and once again, these are all fission processes, is they're actually just one big giant steam turbine. When I learned this as a student, I was actually rather disappointed that we have this very exotic, bizarre nuclear chain reaction going on. And all of that energy is used to literally just spin a turbine. And I'll remind you, that's what wind power does, right? When you see those windmills spinning round and round, those are just big turbines that spin and generate electricity, okay? So now specifically the way that these things work, so you can see we have the reactor core, and those fuel rods are enriched in uranium-235, and they are at a critical mass. However, you have these other devices called control rods. Those are neutron absorbers. So I'll say neutron absorber. So they can actually help limit or regulate the chain reaction. So it limits how much heat is produced in this. And the way that those work, you can imagine these fuel rods, if you want to turn off the reaction, you kind of mesh together those control rods with the reactor core, and those things absorb all of those neutrons. And if you want more reaction to happen, you can kind of lift those up and allow some of those neutrons to escape and create, the chain reaction. And so this is all regulated heavily by a massive amount of technology, right? So you have nuclear reactor operators, people sitting there monitoring this process to make sure it doesn't overheat. So this is actually the process that failed in the Fukushima meltdown as a result of an earthquake. So the controller rods were not able to align with the reactor core, and that's what led to a meltdown. Okay, so now all of that heat gets pumped into a container of water, and an enormous container of water, which creates steam, and that steam hits really, really high pressures and temperatures and is able to spin this turbine and generate power. Okay, so you have to have one of these things next to a large body of water so that, for one, you can keep the system cooled and in check. Okay, so that's your coolant source right here, right? Notice that it's taking in water from this ocean or river or whatever it is, okay? And this is an isolated source of water, right, that doesn't go into the ocean. Or excuse me, that this isolated source of water just stays in this process but does not go into the reactor, okay? So, but also you get water from that same vat, and it is meant to now stay closed cycle within the reactor. Okay, so you have two water cycles going on here. You have the one that's meant to stay in the reactor, and you have the one that's over here kind of keeping everything cool and regulated. And so I have zero problem with using nuclear power. As I've talked about, I think there's an enormous amount of power we can harness out of the nucleus. However, most of these facilities that have had issues are in geologically unstable areas, such as Japan. And so if you get an earthquake or some other type of event that, renders the reactor core inert, the controller rods, or even causes exposure of this water, right? Because this water will have radionuclides. It will be radioactive, okay? Then that can become a big problem. However, there are other ways that we are learning to generate energy from nuclear processes, and that's called fusion. And this is new, and I find very promising, okay? And I'm going to post a couple of videos that, like TED Talk style videos that talk about fusion, as well as micronuclear. So I kind of forgot to mention that. But if you can make this whole thing much smaller and not in a geologically unstable area, this is perfectly fine. This thing will work for years and years and years. And especially if you can go on the micro scale, you can imagine somebody could have one of these things buried under their house, 30 feet down, where you're using just tiny, tiny amounts of material. So that if there were an exposure or if there were some type of event that happened, that tiny amount of material could easily be rendered inert, right? So that's a promising area. And fusion is an extremely promising area. So fusion occurs in the sun. That is where we get all of that massive amount of energy emanating from Sol, right? Sol is the name of our star. So fusion begins with this whole set of chain reactions where protons combine to form deuteriums and positrons, and the whole thing, right, goes crazy. But effectively what you're doing is you're converting a hydrogen into a helium, okay? You're cramming two hydrogens together to make a helium. And if you look at this energy diagram here, so distance between particles, so way out here on this side would be like our two protons well separated, and they're fairly happy in this position. But now as you force them to get closer and closer, okay, they are going to undergo this electrostatic repulsion. And so we could really think of this as like an activation energy, right? We're forcing them to get together, but they don't want to. They're two positively charged protons. But if you can get over this activation energy, you have literally like 10 to the 9 joules, so billions of joules of energy that will get released in the process. So now how is this possible in the sun? Well, there's an enormous amount of gravity that forces those protons together. So the mass of the star is what's driving this process. It forces those protons together through gravity, releases a ton of energy, and the process just keeps going. Hydrogen getting converted to helium. And so when our sun runs out of hydrogen, we're done. It's out of fuel. Hydrogen is our star's fuel. Luckily, that's not going to happen for many billions of years. Okay? So there's a really cool facility right here in California called the National Ignition Facility, the NIF, and that's located at Lawrence Livermore National Lab, so in Livermore in the Bay Area, and they are trying to recreate this process in a laboratory. And I'm not going to spend a lot of time describing in this video because I've already been talking, I think, for too long. But I'm going to post another video about this facility. And this is so cool. To me, this is our path forward for clean energy, the production of helium from hydrogen, both two things that are not toxic at all. We're also running out of helium in the world, so this is a good way to make helium for your, balloons and stuff. But all the same, I would encourage you to go out and find some more information about this and read about it. Okay, folks, that's it. That's all I got. So keep studying, keep learning, keep doing what you are doing. The world needs more scientists and doctors and engineers. The world needs you. We need people like you to get educated and solve these problems. Okay? I hope you enjoyed Chem 110 with me. I enjoyed having you all as students. Hasta luego.